Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous video lecture, I have discussed about unit number 2, that is laser and optic fiber. In this video, I am going to discuss about unit number 3, that is wave mechanics or quantum mechanics. So let's get started. The content of this video are as follows. Let's have a brief of trigonometry. What is waves? Wave motion, properties of waves, types of waves, and finally wave function. In trigonometry, the trigonometric functions are real functions which relate an angle of a right angle triangle to ratios of two side lengths. As shown in this diagram, the most widely used trigonometric functions are the sine, the cosine, and the tangent, and their reciprocals are respectively the cosec, the sec, and the cot. If two right angles have equal acute angles, they are similar, so their side lengths are proportional. The proportionality constants are written within an image sin theta, cos theta, tan theta, where theta is the common measure of 5 acute angles as shown in this diagram. In a right angle triangle ACB as shown in this diagram, an acute angle is A is equal to theta of the hypotenuse. H is the side that connects the two acute angles. The side B adjacent to theta is the side of the triangle that connects theta to the right angle. The third side A is said opposite to theta. Therefore, we can calculate sin theta is equal to A upon H, that is equal to opposite to hypotenuse. Cos theta is equal to B upon H, that is equal to adjacent upon hypotenuse. Tan theta is equal to A upon B, that is equal to opposite upon adjacent, whereas cosec theta is equal to H upon A is equal to hypotenuse upon opposite. Sec theta is equal to H upon B, that is hypotenuse upon adjacent, and finally cot theta is equal to B upon A is equal to adjacent upon opposite. A right angle always includes a 90 degree, that is pi by 2 radians angle, here labeled C. Angles A and B may vary. Therefore, the trigonometric functions specify the relationships among side lengths and interior angles of the right angle triangle. These are the definitions of right angle triangle. Now let's see the relationship to exponential function, that is Euler's formula. Euler's formula relates sine and cosine to the exponential function. Exponential of I theta is equal to cos theta plus I sin theta. This formula is commonly considered for real values of theta, but it remains true for all complex values. Cos theta and sin theta are the real and imaginary part of exponential of I theta respectively. So as shown in this figure, the exponential of I theta is shown. Now let's see the trigonometric functions. In geometric applications, the argument of trigonometric function is generally the measure of an angle. For this purpose, any angular unit is convenient, and angles are most commonly measured in degrees. When using trigonometric function in calculus, their argument is generally not an angle, but rather a real number. In this case, it is more suitable to express the argument of the trigonometric as the length of the arc of the unit circle limited by an angle with the center of the circle as vertex. Therefore, one uses the radian as angular unit A radian is the angle that limits an arc of length 1 on, on a unit circle. A complete turn is thus an angle of 2 pi radians. A great advantage of radians is that many formulae are much simpler when using them. Typically, all formulae relative to derivatives and integrals. This is thus a general convention that when the angular unit is not explicitly specified, the arguments of trigonometric functions are always expressed in radians. As shown in this diagram of circle, trigonometric function sine theta for selected angles like theta, pi minus theta, pi plus theta, and 2 pi minus theta in the four quadrants are shown. The graph of sine function versus angle is shown here. Thus, the angles from the top panel are identified. Sine and cosine relationship to circle is shown in this graphical diagram. So let's see how we can obtain the sine wave and cosine wave with the help of the circle. So this is the animation clip. In the diagram, the green point is rotating with variation in the angle, that is theta is varying, so that we can get the blue wave which is cos theta, whereas the red wave, that is sine theta. This is how we get the sine wave and cosine wave with the help of a circle. More precisely, let's see what are the sine and cosine wave as shown in this graph or the diagram. A sine wave or sinusoid is a mathematical curve that describes a smooth periodic oscillation. A sine wave is a continuous wave and it is named after the function sine, of which this graph is. In this graph, you can see the graphs of sine, that is the solid red wave, and the cosine dotted blue line is there. So these are the functions of sinusoids of different phases. So from this picture, we can have very clear idea what is the sine wave and the cosine wave and what is the difference between them. Ocean is full of waves. One of the first things we need to know about what is wave. What are different types of waves? One shown here in the sea. If we look at the sea waves, we see that they only transfer energy from place to place, not any matter. Wave motion transfers energy from one point to another, usually without permanent displacement of the particles of the medium. Waves transfer energy, not mass. An easy way to see this is to imagine a floating toy duck a few yards out to sea. As the waves propagate, that is travel towards the shore, the duck will not come towards the shore. It may come to shore eventually due to the tides, current or wind, but the waves themselves will not carry the duck with them. A wave only moves mass perpendicular to the direction of propagation. The motion of water waves causes particles to flow different motion, which indicates it has several properties. Let's try to understand the motion of waves and the basic physics behind it. The study of oscillatory motion is basic to physics. Its concepts are required for the understanding of many physical phenomena. The musical instruments like the sitar, the guitar, or the violin, we come across vibrating strings that produce pleasing sounds. The membranes in the drums and the diaphragms in telephone and speaker systems vibrate from about their mean positions. The vibrations of air molecules make a propagation of sound possible. Similarly, the atoms in a solid oscillate about their mean positions and convey the sensation of temperature. The oscillations of electrons in the antennas of radio, TV, and satellite transmitters convey the information. Now let's get introduced about the wave. What is wave? A wave is a disturbance in a medium that carries energy without a net movement of particles. It may take the form of elastic deformation, a variation of pressure, electric or magnetic intensity, electric potential, or temperature. The wave transfers energy, usually involves a periodic repetitive movement. A wave does not result in a net movement of the medium or particles in the medium, that is the mechanical wave. A animated representation of the wave is shown here in this diagram, where the displacement along the y direction we can see, and this is the amplitude as well as the wavelength between the two troughs and crates. So this is a simple definition of the wave, that is, a wave is a disturbance in a medium that carries energy without a net movement of particles. The description of periodic motion in general and the oscillatory motion in particular requires some fundamental concepts like period, frequency, displacement, amplitude, and phase. A motion that repeats itself at regular intervals of time is called periodic motion. Now let's see what is wave motion. Wave motion transfers energy from one point to another, usually without permanent displacement of the particles of the medium. Wave transfer energy, not mass. The example of floating duck on seawater is already I have explained. In this case, up and down motion is illustrated in the figure as below. The animation shows the wave motion, the point along the x-axis analogous to the floating duck at sea. We notice that while it moves up and down, it does not move in the direction of the wave's propagation. Now let's see the properties of the waves. The prime properties of the waves are as follows. Number 1, amplitude. Wave is an energy transport phenomena. Amplitude is the height of the wave, usually measured in meters. It is directly related to the amount of energy carried by a wave. Second, wavelength. The distance between identical points in the adjacent cycles of the crest or a wave is called a wavelength. It is also measured in meters. Number 3, period. The period of a wave is the time for a particle on a medium to make one complete vibrational cycle. As the period is time, hence it is measured in units of time such as seconds or minutes. Next property of waves is frequency. Frequency of a wave is the number of waves passing a point in a certain time. The unit of frequency is hertz, which is equal to 1 wave per second. The period is the reciprocal of a frequency and vice versa. So period capital T is equal to 1 upon frequency, that is f. Or we can write frequency f is equal to 1 upon capital T, that is period. Fifth property is speed. The speed of an object means how fast an object moves and is usually expressed as a distance traveled per time of travel. The speed of a wave refers to the distance traveled by a given point on the wave, that is crest, in a given interval of time. That is, speed is equal to distance upon time. Therefore, we can write the equation V is equal to C is equal to x upon t. Speed of a wave is thus measured in meter per second. Now let's see the types of the waves. A wave is disturbance that propagates or moves from the place it was created. There are 3 basic types of the waves. First is mechanical waves, second electromagnetic waves, and third one is matter waves. So let's see one by one in detail with their subtypes. Now let's see first electromagnetic waves. Electromagnetic radiation or EM radiation or EMR refers to the waves or their quanta or photons of the electromagnetic field propagating or radiating through the space, carrying electromagnetic radiant energy. It includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. We have already discussed electromagnetic waves in detail in unit number 1. Electromagnetic waves can travel through a vacuum at the speed of light, that is V is nothing but the C is equal to 2.99792458 into 10⁸ meter per second. For example, light from distant stars travel through the vacuum of space and reaches Earth. As shown in the diagrams, electromagnetic waves can be imagined as a self-propagating transverse oscillating wave of electric and magnetic fields. This three-dimensional diagram shows a plane linearly polarized wave propagating from left to right as shown in this animated figure. Next type of waves is mechanical waves. Mechanical waves are governed by Newton's laws and require a medium. A medium is the substance a mechanical waves propagates through, and the medium produces an elastic restoring force when it is deformed. Mechanical waves transfer energy and momentum without transferring mass. Some examples of mechanical waves are water waves, sound waves, and seismic waves. The medium of water waves is water. For sound waves, the medium is usually air. Mechanical waves exhibits characteristics common to all waves, such as amplitude, wavelength, period, frequency, and energy. The simplest mechanical waves repeat themselves for several cycles and are associated with simple harmonic motion. These simple harmonic waves can be modeled using some combination of sine and cosine functions. The crest is the highest point of the wave and the trough is the lowest part of the wave. The time for one complete oscillation of the up and down motion is the wave's period, that is capital T. The wave's frequency is the number of waves that passes through a point per unit time and is equal to F is equal to 1 upon capital T. The period can express using any convenient unit of time but is usually measured in seconds. Frequency is usually measured in hertz, where 1 hertz is equal to 1 per second. So this is we have already discussed before. After the discovery of radio waves, the Hertz, the scientist's name, in 1857 to 1894, a special name has given to the unit of frequency. It is called Hertz, abbreviated as capital H and then small z. Thus, 1 Hertz is equal to 1 oscillations per second. Note that the frequency f is not necessarily an integer. The magnitude of wave velocity is the distance the wave travels in a given time, which is one wavelength in the time and one period, and the wave speed is the magnitude of wave velocity. Therefore, the equation form is v is equal to lambda upon t, or v is equal to lambda f. The picture shows ripple in water is a surface wave, which is nothing but a mechanical wave. So this is one of the example of mechanical waves. Now let's understand the concept of pulse, which is important to understand mechanical waves. Periodic waves described by their characteristics of wavelength, period, amplitude, and wave speed of the wave. Waves can also be described by the motion of the particles of the medium through which the waves move. The position of particles of the medium can be mathematically modeled as wave functions, which can be used to find the position, velocity, and acceleration of the particles of the medium of the wave at any time. A pulse can be described as a wave consisting of a single disturbance that moves through the medium with a constant amplitude. The pulse moves as a pattern that maintains its shape as it propagates with a constant wave speed. Because the wave speed is constant, the distance the pulse moves in a time delta t is equal to delta x. That is, delta x is equal to v delta t. So as shown in this figure, the pulse at time t is equal to 0 is centered on x is equal to 0 with amplitude a. The pulse moves as a pattern with a constant shape with a constant maximum value, that is capital A. The velocity is constant and the pulse moves a distance delta x is equal to v delta t in time delta t. The distance traveled is measured with any convenient point on the pulse. So in this figure the crest is used. So the position and the behavior of the pulse is shown in this animated figure. Now let's see transverse waves. Mechanical waves can be transverse or longitudinal depending on the relation between the directions of the disturbance or the displacement in the medium and that of the propagation of wave. To differentiate between them, let us consider the response of stretched string fixed at one end. If you give a single up and down jerk to the free end of the string as shown in figure A, a wave in the form of single pulse travel along the string. The net result is that a distortion in the shape of string, that is the pulse, moves along the string with a certain velocity, let's say small v. If you move your end up and down in continuous manner, a continuous wave travels along the string with a velocity v. However, if the motion of your hand is sinusoidal function of time, at any given instant of time, the wave will have a sinusoidal shape as shown in figure B. The wave has the shape of sine or cosine curve. The waves shown in figure B can be studied in two ways. One way is to monitor the waveforms as they move to the right, that is the perpendicular position on the string, and monitor to the motion of an element that at that point as it oscillates up and down while a wave passes through it. We would find that the displacement of every such oscillating string element is transverse, that is perpendicular, to the direction of travel of the wave as indicated in this figure. Such wave is said to be transverse wave. A simple mechanical wave consists of a periodic disturbance that propagates from one place to another through a medium as shown in this animated figure A. The wave propagates in the horizontal direction, whereas the medium is disturbed in a vertical direction. Such a wave is called a transverse wave. In transverse wave, the wave may propagate in any direction, but the disturbance of the medium is perpendicular to the direction of propagation. Therefore, the transverse wave are waves where the vibrations are perpendicular to the direction of propagation as shown in figure B. Transverse is a fancy word for perpendicular. Now let's see longitudinal waves. Let's consider the production of waves in a long air-filled pipe by the movement of piston as shown in figure. If you suddenly move the piston to the right and then to the left, you are sending a pulse of pressure along the pipe. The motion of the piston to the right pushes the elements of air next towards the right, which changing the air pressure there. The increased pressure in this region then pushes on the elements of air somewhat farther along the pipe. Moving the piston to the left reduces the air pressure next to it. This causes the elements of air next to it move back to the left, and then the farther elements follow. Thus, the motion of the air and the change in air pressure travel towards the right along the pipe as a pulse. If you push or pull on the piston in a simple harmonic manner, a sinusoidal wave travels along the pipe. It may be noted that the motion of the elements of air is parallel to the direction of propagation of wave. This motion said to be longitudinal, and the wave produced is therefore called a longitudinal wave. The sound waves produced in air are such pressure waves and are therefore longitudinal characteristics. So this is one of the example, that is sound waves are longitudinal waves. Longitudinal waves cause the medium to vibrate parallel to the direction of the wave. It consists of multiple compressions and rarefactions. The rarefraction is the farthest distance apart in longitudinal wave, and the compression is the closest distance together as shown in figure A. Figure A shows an example of longitudinal wave. The size of the disturbance is its amplitude A and is completely independent of the speed of propagation, that is v. Longitudinal waves are the waves where the vibrations are parallel to the direction of propagation, where the vibration causes the particles to be bunched together, that's a compression. Where they are farthest apart is a rarefraction as shown in figure B. One more type of wave is surface waves. This type of wave travels along the surface or interface between the two medium. An example of surface waves would be waves in a pool or in an ocean lake, or any other type of water body. So this is the picture which shows the surface waves in water, showing water ripples. Next type of wave is trochoidal waves. Trochoidal waves are kind of like a combination of longitudinal and transverse waves. The vibrations are circular because they occur both parallel and perpendicular to the direction of propagation. They look like transverse waves. For example, water waves, as shown in this diagram. The motion of water waves causes particles to follow clockwise circular motion. This is a result of the wave having both transverse and longitudinal properties. So here is a one floating object and elliptical trajectory it shows. So this is the wave propagation and on the surface of the ripples. So surface waves on the ocean or a pond or in a cup of water, etc. are trochoidal waves. Next type of wave is standing waves. A standing wave, also known as a stationary wave, is a wave which oscillates in time but whose peak amplitude profile does not move in space. The peak amplitude of the wave oscillations at any point in space is constant with time, and the oscillations at different points throughout the wave are in phase. The locations at which the absolute value of the amplitude is minimum are called nodes, and the locations where the absolute value of the amplitude is maximum are called antinodes. As shown in this figure, the animation of standing wave, that is in red color, created by the superposition of left traveling blue wave and right traveling, that is the green wave, is shown. Now here we come, the most important part of our unit, that is matter waves. Matter waves are a central part of the branch of physics known as quantum mechanics. These waves are associated with protons, electrons, neutrons, and other fundamental particles found in nature. The theory that all types of matter waves have wave-like properties was first proposed by Louis de Broglie in 1924. A moving particle is associated with a wave is called matter wave or de Broglie wave. Being an example of wave-particle duality, all matter exhibits wave-like behavior. For example, a beam of electrons can be diffracted just like a beam of light or water wave. In most cases, however, the wavelength is too small to have a practical impact on day-to-day activities. Hence, in our day-to-day lives, with objects the size of tennis balls and people, matter waves are not relevant. The de Broglie wavelength is the wavelength, that is lambda, associated with a massive particle, that is the particle with mass as opposed to a massless particle, and is related to its momentum, that is p, through a Planck's constant, that is h. So we have equation wavelength lambda is equal to h upon p. So which can be written as lambda is equal to h upon mv. The demonstration of matter waves in diffraction of electrons is shown in this animated figure. So from this explanation, one important point is clear that a moving particle is associated with a wave is called matter wave, or simply we can say de Broglie wave. Now let's see one-dimensional sinusoidal wave function. Let us consider a particle vibrating back and forth about the origin of an x-axis between the limits plus a and minus a as shown in this animated figure. A particle vibrating back and forth about the origin of x-axis between the limits. In between these extreme positions, the particle moves in such a manner that its speed is maximum when it is at the origin and 0 when it is at plus and minus a. The time t is chosen to be 0 when the particle is at plus a position and returns to plus a position at t is equal to capital T. To study the motion of this particle, let's record its positions as a function of time by taking snapshots at regular intervals of time. A set of such snapshots is shown in this diagram. A sequence of snapshots taken at equal intervals of time showing the position of a particle at its oscillates back and forth about the origin along the x-axis between the limits plus and minus a. The length of the vector arrows is scaled to indicate the speed of the particle. The speed is maximum when the particle is at the origin and 0 when it is at plus minus a. If the time t is chosen to be 0 when the particle is at plus a, then the particle returns to plus a at small t is equal to capital T, where capital T is the period of the motion and the motion is then repeated. The position of the particle with reference to the origin gives its displacement at any instant of time. For such a motion of the displacement x of t of the particle from a certain chosen origin is found to vary with time as x of t is equal to capital A cos of omega t plus phi. So in this equation, x of t is a displacement, that is equal to capital A is amplitude into cos of omega t, which is angular frequency, plus phi, which is phase constant. So omega t plus phi is nothing but the phase. The motion represented by this equation is called simple harmonic motion, that is SHM, a term that means the periodic motion is a sinusoidal function of time, equation in which the sinusoidal function is a cosine function is plotted in this figure. We shall now define these quantities. The quantity A is called the amplitude of the motion. It is a positive constant which represents the magnitude of the maximum displacement of the particle in either direction. The cosine function in the equation varies between the limits plus minus 1, so the displacement x of t varies between the limits plus minus capital A. In figure A, the curve 1 and 2 are plots of equation for two different amplitudes A and B. The difference between these curves illustrates the significance of amplitude. The time varying quantity, that is omega t plus phi, in equation is called the phase of the motion. It describes the state of motion at a given time. The constant phi is called the phase constant or phase angle. The value of phi depends on the displacement and the velocity of the particle at small t is equal to 0. This can be understood better by considering figure B. In this figure, the curve 3 and 4 represents plots of equation for two values of the phase constant phi. It can be seen that the phase constant signifies the initial conditions. The constant omega, called the angular frequency of the motion, is related to the period capital T. To understand the concept of waves, one important parameter is there, which is simple harmonic motion. Very often the body undergoes periodic motion, has an equilibrium position somewhere inside its path. When the body is at this position, no net external force acts on it. Therefore, if it is left there at rest, it remains there forever. If the body is given a small displacement from the position, a force comes into play which tries to bring the body back to the equilibrium point, giving rise to oscillations or vibrations. There is no significant difference between oscillations and vibrations. It seems that when the frequency is small, we call it oscillation, like the oscillations of a branch of a tree. While when the frequency is high, we call it vibration, like the vibration of a string of musical instrument. Therefore, the simple harmonic motion is the simplest form of oscillatory motion. This motion arises when the force on the oscillating body is directly proportional to its displacement from the mean position, which is also the equilibrium position. Further, at any point in its oscillation, this force is directed towards the mean position. Let us consider the motion of a reference particle P as shown in figure, executing a uniform circular motion with constant angular speed omega in a reference circle. The radius a of the circle is a magnitude of the particle's position vector. At any time t, the angular position of the particle is omega t plus phi, where phi is its angular position at t is equal to 0. The projection of particle p on the axis x-axis is a point p prime, which we can take as a second particle. The projection of the position vector of the particle p on x-axis gives the location x of t of p prime. Thus we have equation x of t is equal to a cos of omega t plus phi, which is the same as one-dimensional sinusoidal wave function equation. This shows that if the reference particle p moves in a uniform circular motion, its projection particle p prime executes a simple harmonic motion along a diameter of the circle. In a more formal language, we can say that simple harmonic motion is the projection of uniform circular motion on a diameter of the circle in which the latter motion takes place. Now let's see the simple harmonic wave function. In simple harmonic motion between y is equal to plus a and y is equal to minus a with a period capital T, the wave is sinusoidal and is translating in the positive x direction as time progresses. Let's recall from your study of algebra that if f of x is some function, then f of x minus d is the same function translated in the positive x direction by a distance small d. The function f of x plus d is the same function translated in the negative x direction by a distance small d. We want to define a wave function that will give the y position of each segment of the string for every position x along the string for every time t. From first snapshot, the y position of the string between x is equal to 0 and x is equal to lambda can be modeled as a sine function. This wave propagates down the string one wavelength in one period as seen in the last snapshot. The wave therefore moves with a constant wave speed of v is equal to lambda upon t. Let's recall that a sine function is a function of the angle theta oscillating plus 1 and minus 1 and repeating every 2 pi radians. However, the y position of the medium or the wave function oscillates between plus a and minus a and repeats every wavelength lambda. So as shown in this diagram, a sine function oscillates between plus 1 and minus 1, repeating every 2 pi radians. Consider the ratio of the angle and the position theta upon x is equal to 2 pi upon lambda. Hence, theta is equal to 2 pi upon lambda into x. Therefore, using theta is equal to 2 pi upon lambda into x and multiplying the sine function by the amplitude capital A, we can now model the y position of the string as a function of the position x. Therefore, we can write y of x is equal to a sine of 2 pi upon lambda into x. The wave on the string travels in the positive x direction with constant velocity v and moves a distance vt in a time t. The wave function can now be defined by y of xt is equal to a sine of 2 pi upon lambda into x minus vt. Therefore, it is often convenient to rewrite this wave function in a more compact form. Therefore, by multiplying through by the ratio 2 pi by lambda leads to the equation y of xt is equal to a sine of 2 pi by lambda into x minus 2 pi by lambda into vt. The value 2 pi by lambda is defined as the wave number. The symbol for the wave number is a small k and has units of inverse meters. The angular frequency is defined as omega similar to 2 pi upon t. The second term of the wave function becomes 2 pi upon lambda into vt is equal to 2 pi upon lambda into lambda upon t into small t. That is equal to 2 pi upon capital T into small t is equal to omega small t. Hence, the wave function for a simple harmonic wave on a string reduces to y of xt is equal to a sine of kx minus plus omega t, where capital A is the amplitude, small k is equal to 2 pi by lambda is the wave number, and omega is equal to 2 pi by capital T is the angular frequency. The minus sign is for waves moving in the positive x direction, and the plus sign is for waves moving in the negative x direction. The velocity of the wave is equal to, hence, v is equal to lambda upon capital T, that is equal to lambda upon capital T into 2 pi by 2 pi, that is multiplying and dividing by 2 pi. Then we get v is equal to omega upon k. Think back to our discussion of a particle when the position of the mass was modeled as x of t is equal to capital A into cos of omega t plus phi. Hence, the angle phi is a phase shift added to allow for the fact that the mass may have initial conditions other than x is equal to plus capital A and v is equal to 0. For similar reasons, the initial phase is added to the wave function. The wave function modeling a sinusoidal wave following for an initial phase shift phi can be written as y of xt is equal to a sine of kx minus plus omega t plus phi, where y of xt is a vertical position, capital A is amplitude, small k is angular wave number, small x is horizontal position variable, omega angular frequency, small t time variable, and phi is a phase. The value kx minus plus omega t plus phi is known as the phase of the wave, where phi is the initial phase of the wave function. Above equation is known as simple harmonic wave function. This is all about the trigonometry, wave motion, properties of the waves, types of the waves, and wave function. In my next lecture video, I will discuss about wave-particle duality and de Broglie's hypothesis. So don't miss my next video lecture. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.